Okay. I'm gonna review what we've done so far in this unit. So basically, we're dealing with rotating objects, and I'll just draw a picture of a disk. And so we're going to spin this thing around. Okay. Now, we applied a torque to this. We apply a torque. That's a twisting force. Okay. And a torque is equal to a, well, let's say I apply a force on the outside like this. It's a tangential force, F sub t, a tangential force, and of course this has some radius, this disk, r. So in this case, the torque would just be the radius times that tangential force. And the result of applying a torque like this, and let's say the torque is constant. Maybe this is a cord that's been wrapped around and you're pulling on it or something like that. The result of applying a net torque to an object is that it will angularly accelerate. It will change its rotational motion. And the amount of angular acceleration you get depends on how massive this thing is and how that mass is distributed around the axis of rotation. We take that combination of mass and axis of rotation, distance from axis of rotation, and we come up with an expression for it that we call rotational inertia. Okay, and so torque equals force times lever arm, this force times this lever arm distance, and that's going to be equal to the rotational inertia of your object times the angular acceleration. Now, if your torque is constant, if this is constant and your rotational inertia is constant, then your angular acceleration will be constant. And if that's true, then you have what we call the kinematic equations for rotational motion that is very similar, almost identical to the kinematic equations we had for constant linear acceleration. And that would be omega equals omega naught plus the angular acceleration times time. The change in angular position is equal to the final plus the initial angular velocity divided by 2. This is my average angular velocity times time. Or my change in angular position is equal to my initial angular position times time plus 1/2 my angular acceleration times the time squared. And finally, whoops, I always do that. The final angular velocity squared equals the initial angular velocity squared plus twice the angular displacement times the angular acceleration. And these are the kinematic equations that, and I think you notice they look just like the ones that we did before. And these are analogous variables here. This is like velocity, delta x, this is like, a, acceleration. The equations are all very, very similar. And in fact, if you look at this equation where torque equals I alpha, well, isn't that a lot like force equals mass times acceleration? Yes, it is. It's just the rotational equivalent of that. Okay. Now, if you solve for angular acceleration using this equation, your angular acceleration will be in terms of radians per second squared. And that's because of this r right here. This is the radius, and it's kind of like the r is like how much angle you can think of r as like meters per radian. You go around this many meters per radian of rotation. Okay, but anyway, you can use these though for anything. You can use these with, so this is always in radians per second squared, always. But you can convert it to the other ways of measuring angle, and we have a unit conversion for that. Like this can be in, this all can be in radians, or it can be in degree. Well, let me just say 2 pi radians is equal to 360 degrees, and this is equal to 1 revolution. And so this is your conversion factor that we talked about. And in fact, these equations can work in revolutions or degrees or radians. But this equation here only works in radians. There are certain equations that only work with radians. So when in doubt, put your angles in radians and you'll be able to solve it. Okay. What else did we do? We also talked about the equations that relate like this object, right? Let's say you put a little ant. We've got an ant problem in our classroom right now. If I put a little ant on this spinning disc, right? How fast is this ant moving? How fast is, what is this ant's angular displacement? What is the ant's acceleration and so on? And we can relate rotational motion to linear motion or rolling motion in this way. We said that a delta S is my arc length. It's a distance. Delta S is really a distance, right? It's not a displacement so much as a distance traveled from here over to here. It's an arc length. Well, that's going to be equal to R times delta theta. That is, if you know what delta theta is in radians and multiply it by R, the radius, you'll get your displacement. Now, if you divide both of these by delta t, both sides by delta t, you get the equation for velocity, or speed, really. The speed of going around in circles will be r omega, and the tangential acceleration is going to be equal to r times alpha. So you can see that all you're doing is you're taking your rotational quantities for position, velocity, and acceleration, and just multiplying it by the radius, or its lever arm, or the distance from the axis of rotation to the object you're looking at, and multiplying, and you get these. Now, of course, these are all in radians. Radians. They must be in radians, or these equations don't work. There is another acceleration to worry about, and that is the radial, or also called the centripetal acceleration that we talked about earlier in the year. And I'm not going to rederive it, but there's a couple of expressions for it. You can go r omega squared, and then, yeah, and well, I'll just leave it like that. There's another one, I think it's v times omega, which is really weird, but somebody used that on the homework the other day. But in any case, you can always use this. Okay, and remember, this is the acceleration. This is the acceleration that changes direction. And this is the acceleration that changes speed. Remember, a tangential acceleration will change the speed that you're going around in a circle. You're slowing down or you're speeding up as you go in a turn. That's a tangential acceleration. But, you still have that centripetal acceleration, that acceleration that's changing the magnitude of your direction. Okay, so, one last thing. We talked about energy, kinetic energy. And kinetic energy, remember we had the linear kinetic energy. Well, that's equal to 1/2 the mass times your velocity squared. But what if this massive moving object was like this little ant was moving around in a circle. Sure, it's still got kinetic energy, but how do we express that kinetic energy in terms of its angular velocity instead of linear velocity? Well, rotational kinetic energy is 1/2, but instead of mass, we have rotational inertia times omega squared. Now, if all you had was a particle here, an ant going around, the rotational inertia is easy. It's just the mass of the ant, m, times r squared. Okay, yes?
Is inertia just given, or do you make like on that?
And the question was, will rotational inertia be given?
So it's just like, you know the inertia that you put in your
Yeah.
equation? Is all that just given?
Yeah.
Oh, really? It looks
Well,
like it's
well, okay, look. So the question is, will this be given, or do you have to find it? I mean, how do you know what I is, right? Well, for a disk, let me zoom out a little bit here. If I give you a big shape, like a rotating bowling ball, like if I took a bowling ball and I spun it on its axis, there is an equation that allows you to find the rotational inertia, and that would be 2/5 mr squared. This is a disk, okay? So this disk has a rotational inertia equation 1/2 mr squared. If I took a stick, I'll use this. Yeah. Thank you. So if I'm rotating this about its center, this is 1/12 ml squared. L is this doesn't have a radius, does it? But it has a length. So if I rotate it about its center, okay, it's the rotational inertia is 1/12. Now how do you know that? It's in a table in your book on page 208. You have to look it up. Or on an exam, what would I do?
Give it to me.
I would give it to you.
Oh, good.
Okay? So, or I would give you all the information you need to solve for it. You know, you can solve for it.
So like the basic equation
Yeah.
is I equals mr squared?
Well, I equals some fraction of the object's mass times r squared. Now, r is a good letter to use when it has some kind of roundness, like a disc, right? Or a sphere. But what about a stick? A stick doesn't have an r, but it has a length, L. So we'll use it. Wait, capital L. Oh, yeah, it's like this. All right, so you would use an L for that. But what goes here? It depends. Now, in AP Physics C, we actually go through the calculus to determine what that fraction should be. In this class, we don't use calculus, so it's just derived for you. It's in the book. Okay? But look, it always has units of kilograms times meter squared. I will always be some number times kilogram meter squared. Okay? So this is kind of what we did so far. So I think this now, and yeah, I think you can use. Yes, quick question.
What do you think the test will be?
Okay, I'll answer that question. Oh, yeah, capital iota. Thank you. Yeah. All right. That is all. Oh wait, not all. Okay, now it's all.